Okay, day 142 about batteries. First of all, the notes, and then we'll go on to a couple of labs. Regular batteries are alkaline batteries. They are a type of battery which derives its energy from a reaction between zinc metal and manganese dioxide. These alkaline batteries came out in the 50s, and they were the first really long-use batteries. Before that, they had other kinds of batteries that used different kinds of materials on the inside, but they didn't last terribly long. They didn't get a lot of use in many different things. Rechargeable batteries came out after the 50s, and one example is lead acid, and those are for regular old cars, regular gasoline-powered cars. This kind of battery helps run the little electric motor that starts the car. Lithium-ion or nickel-cadmium batteries, they're the ones that are used in our phones, laptops. The electric cars that run completely on electricity use lithium-ion as well, although there are new kinds of batteries that are coming out for those kinds of cars. The first big use that made batteries really popular with adults were flashlights, and that was about 100 years ago. So imagine that before that, people had to walk around with kerosene lanterns, and those were kind of bad. The risk of fire and all that was significant. The first big use of batteries for kids was little toy trains, and later on the cars and all that. When we look at a battery, we have one end that has a little bumpy end, and we have the other end that is nice and flat. It's the flat end that is negative. So when you hook this into a circuit, the electrons leave this end and go out and come around, and they enter into the bumpy end. Or if you go with the convention that most electronics go on nowadays, they talk about a positive charge. And so the positive current leaves the bumpy end and goes around to the flat end. You can always remember that because on the end of the battery there's a little plus mark there. Here's a better one that's a little bit easier to see. There's a little plus mark to remind you on that. You can't recharge all batteries, only the rechargeable batteries, lithium-ion, nickel-cadmium. You can't recharge the older versions of batteries because when you reverse the chemical reaction of zinc and manganese, hydrogen gas is produced, and that's not a good thing. You don't want this gas to build up pressure on the inside and then burst a seam, and then you have all this nasty chemical stuff coming out all over the place. Okay, battery lab. Part 1, voltaic pile. Task, make a primitive battery. Materials, coins, vinegar, meter, beaker. Procedure C to the right. Okay, so there's this procedure here. We are going to hook up 2 wires to a stack of coins. And the stack is going to be alternating penny, nickel, penny, nickel, penny, nickel, penny, nickel. And we're going to have these little pieces of paper in between every layer that's soaked in vinegar. And so the vinegar and the copper of the pennies and the zinc of the silver coins, whether they be nickels or dimes or quarters, anyway, those 3 materials have a chemical reaction that will release electrons, and those electrons then can flow through the wires. So let's see how that goes. Here's the vinegar, and we have our meter, and we have a bunch of coins. We're not going to make a huge amount of electricity, but we are going to have it enough so that the meter can be seen to wiggle just a little bit. And make wet towel pieces. The more paper towels we have soaked, the better the electricity current is going to be. Okay, let's see if that is enough to make the needle move just a little bit. So I hold the wire on one end, and then on the other end. There you can see the needle moving. It's just a tiny bit. If I had more patience and I would add more coins to the stack, it might move a little bit more significantly. Most of the time, that's all that it moves. But I have had people have the needle move a centimeter or so. I don't know what the magic is. It might be due to the corrosion of the coins. They're kind of dull and rusted because of these chemical reactions that are going on, but that's not terribly important as to why. Okay, the next little activity here is battery size versus voltage task. I will answer the question, how does the size of a battery affect the voltage? Is it true that the bigger the battery, the more voltage? Materials, batteries, and a multimeter. Arrange the batteries in order from smallest to biggest. So here we have a little coin battery that's from my digital scale at home in my kitchen. Here is a little N battery that's from my garage door opener. AAA battery from a grapher calculator. AA battery from 1,000 different uses. And then we have this square battery. And then we have this biggest battery. It's called a D-size battery if you're not familiar with that. This is oftentimes used in flashlights nowadays. Okay, step number 2, set the multimeter to the voltage setting. It's expected that all the voltages will be less than 10 volts. So, I turn this and I can put it on the 20. I'll put it on the 20 setting. Everything's going to be less than 20. I don't want to put it on the 2 because there might be a battery in there that's more than 2 volts. Okay, number 3. Place one multimeter probe on each end of the battery, read the voltage, and then we'll see what the results are. Okay, the coin battery. Oh my goodness sakes alive. What a clumsy person. Okay, here's the smallest one. The smallest one is reading right there. The next smallest. There's the reading there. The next smallest. There we go. Now it's a steady number. Okay, that's the AAA. Now the AA. I have a hard time holding these in the right place. Okay, there we go. There's a fairly steady value. Here's the square battery. And then finally the biggest battery. Okay, so that was the D cell. Before that was the square battery, and then the AA, AAA, N, and I believe it's called a CR battery for the little tiny coin batteries, CR something something something. Okay, that's the end. There's some reading to do in your packet.